Okay, we are going to uh, share my screen. Before starting today's lecture, I'd like to uh, talk about the exam one first. Many students contact me and ask if this paper is okay or not, but I already uh, announced that. mm, the important thing is the evaluation. You need to mention how you the what's the problem, what's the issues in the papers, and then second one is how they calculated the work circles and how this result can deliver the material design or material property. So you need to mention all of them. But if you mention everything, there is no problem. If you selected paper or any other the materials, totally fine. Then this is my comment. And um, do you did you see the Miller's index and crystal reflections? If you people, I would like to talk with, I'd like to discuss one more thing. In fact, uh, our based on the syllabus, we have one more presentation. Is instrument presentation. Paper exam two. Paper exam two, we have a presentation one. It is related to the instrument. Once I make it, once I organized this syllabus, I expected very few students uh, might assign this class. So I think the individual presentation might be okay. However, we have total is 17 students. So I wonder if you guys have their own uh, instrument presentation, the presentation time is very short. It's 7 or 8 minutes. I don't think it can deliver lots of things, the principle of instrument and how we can use this one or how to operate them, uh, lots of things. So um, what do you think about the which one do you prefer? You guys should just prepare the presentation individually, or do you want to prepare teamwork? So I think you cannot decide right now. So you don't need to decide today. Um, if you are available, please email me about your opinion, the teamwork or uh, the individual presentation. Team or individual. Until next Tuesday. So according to your opinion, I will decide individual presentation or team presentation for presentation one, instrument presentation. Okay, and did you see the mirror index of crystal reflect symmetry, crystal symmetry? Yeah, I would like to briefly explain the mirror index and crystal symmetries. If you have any question, please see my recording, but my recording is not, if my recording is not good, please contact me by email or uh, ask a Zoom meeting. So mirror index is yeah, as you can see, this is the mirror index, and then it can deliver the uh, how to define the face of the crystal structures. So this is the rule how to the define the mirror index. Initially, you need to set up the axis and then normalize the intercept first and invert the intercept like that. If for example, it's 2, 3, 1, once we invert it intercept, we got the 1/2, 1/3, and 1. Then we can multiply the integer, then we can add the 3 to 6. So it will be 3 to 6. If there is a kind of a negative intercept, we kind of use the bar over the values, the vectors. Or if there is the infinite intercept, it's really easy. So if you see the 1 over infinity, 1 over infinity is 0. So we can easily calculate it like that. Why the mirror index is important in our mechanical engine mechanical properties, the shear stress, which just stress or normal stress. It is related to the normal vector of the surface, normal vector. So uh, normal vector is if we have this plane, our normal vector indicated the perpendicular vector of the display. So if we calculated the cost vector of the R1 and R2, the normal vector could be obtained like it is exactly related to the mirror index. So using the mirror index, we can easily calculate the normal vector. So normal vector is related to the normal stress. So we can make the correlation between them. So this is an example of this mirror index with a different surface. Please try to calculate them yourself. Then you can understand the mirror index easily. Symmetry is the if we rotate it or if we make it a kind of mirror plane inverse, we can make the same position. So in this case, if we rotate like if we rotate it, if we rotate like that, we can make it the same, right? Same. It is rotational symmetry. The order of rotational symmetries can be easily calculated by 360 or divided by angle of rotation. So in this case, if we rotate if we consider just Q, and then if we rotate 90 degrees, 180 degree, 270 degree, we can make it the same, same with this field. So to make it order 4. So the scale has order 4, but in case of the triangles can give 120 degrees series, 120 degrees rotation, and 120 to 40 degrees to 40 rotation to make it symmetries. So they have the 43 rotation symmetry because 120 divided by 360 divided by 110 symmetries. 3. And then this pentagon, hexagon, we have the 5 and 6. You can try to calculate them. And there I'm going to move on to this one. This is a cube. So if we define the PQ axis for the rotational symmetry, we can get the order 4. But if we just focus on the 5-fold rotation, this scale, if we focus on the AB for the rotational symmetry, we have the 5-fold rotation symmetries because this is the top view, and then can rotate it like a rotation. So we have a 5-fold. But if we make the rotational symmetry like a PQ line, we have only two. So this is the symmetries, order of symmetries for the cube. This is the cube. And there is some different axes. So try to estimate it. Try to calculate the order of rotation symmetries. And then this is tetrahedron. Tetrahedron has 7 different axis of rotation symmetries. This is a 2-fold, this is 3-fold. And this is a mirror symmetries. And if you see, there is a completely same symmetries. And so, just to think about these triangles, based on this plane, they have the exactly same as the mirror symmetries. And P is exactly the same. So I brought some of the examples A, B, C, D, E, F, G, H, and just to try to how many mirror plane you can find. So I gathered that I already put the answer here. Just try yourself. So for example, this is the mirror plane like that, and then make 1 mirror. So if we prepare the very nice cube with the triangle edges, they have the middle plane and four-fold plane here. If we focus on the top view, we have the four-fold axis and middle plane. So, well, if we see if we consider the edge of this samples, we have the 3-fold axis, 120 degrees C rotation. And then if we focus on the edge, this is the point, this is the edge. We can find the middle plane here and here. Then what is an inversion center? Inversion center is exactly inverse based on the one point. It is simply related to x, y, z is minus x minus y and minus z. So if we use the bracket, it's exactly minus x minus y minus z, and then it is described like that. So if you use the inverse, if you, there is a, if you want to describe the inverse symmetry, you need to put this one. But the number is defined another way. Now let me explain this part later. Uh, this is the rotation axis with mirror frame. The N indicates the mirror frame, and 1, 2, 3, 4, 6 is the rotation, order of rotation axis. So you can see there is a 2 order, 3 order, 4 order, 6 order. And then with perpendicular mirror frame, it means because over there we mentioned we write down N. And then this is a root inversion. Root inversion is rotate rotated at certain degree, then invert. So rotate and inversion. Rotate and inversion. So if we rotate 180 degrees C, we can describe two order rotation and inversion. This is inversion. Inversion. So we can have the three or two inversion and 1, 2, 3, 4, 6 with the inversion case. So you see is mirror plane. 1, 2, 3, 4, 6 is the rotational axis of the 1, 4, 2, 4, 3, 4, blah 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 blah. And go to inversion axis 1, 2, 3, 4, 6. And I is just inversion. So just to try to do your the yeah, I think so. Yeah, I think you can see and then uh, I uploaded it and then just let me know if you have any difficulties to understand the symmetries and mirror index. But the reason why mirror index and symmetry is important the importance of this one is we can minimize the metrics, the tensor metrics, uh, variance or stiffness metrics. You see, if you use focus on the triclinic, triclinic, monoclinic, ortholonic is crystal structure. So this is the crystal structure of the triclinic. Monoclinic, also rhombic, tetragonal, hexagonal, and cubic. Cubic is very simple. It's all side ends of the screen is same, and they have the 90 degrees. The triclinic is very complicated. A, B, C, and D, not of the 90 degrees. So, based on the algorithmic crystal structures like this system, we can reduce the tensor. Um, in case of the hexagonal or cubic, we can decrease. I would like to mention this one first. The small dot indicates 0, and large dot indicates non-zero component. And if we make the line, the while the two both that have the equal components. Um, but if the solid dot and the what is open dot, it's one indicates numerically equal but opposite. And then this one, you can see this one and this one. I will explain this later. So in case of the hexagonal system or cubic system, we minimize the tensor size given the contours so we can calculate very easily. Uh, but we need to put method things in case of the pipe things. Do you? Yeah. So so this is the cubic system, cubic symmetric and elastic functions. So if we focus on the stress on 1, 0, 0 direction, what is this one is the related to the 0, 1, 0 or 0, 0, 1 axis. So we can make it the C11 equal to C22 and C33. And then shear stress also equivalent, so equivalent to the around the bar the this axis. So C44 equal to C55 and C66. And C12 equal to C13 and C23. So we can have this one. So we have the independent elastic constants for those cubic material is only 3. Also, we can indicate indicate anisotropic issues using the Janus ratio. Janus ratio can be expressed by like it, C11 minus C12 divided by 2C44 or this one. So if the Janus ratio is 1, the material is exactly isotropic. So based on these relations, we can make this one is C11, C11, and this is a C12, C12, C12. And this is a C44, 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 and C44 is related to C11 and C22. So we can simplify this answer. Then we can make it simplify the relations like that, and then elastic property of the materials simplify like that. So Poisson ratio, elastic modulus, or modulus can be expressed like can be expressed by the tensors.
I have a question.
Mm-hmm.
What is S11? Is it equal to C11? All right.
No,
Okay. Okay, I missed
no, no,
this
no, no,
part.
no.
Okay.
Let me explain. Let me clear. C11 and there is a correlation effect. That is this thing. It is C is. I think I made a mistake. So, if you see this one, the C is the related to the C, and strain is related to the stress. and strain would be expressed by the stiffness and stress. So it's different. Do you understand? Not too much different. Different.
So the S is equal to the C over 1.
Not equal because it's tensor.
Okay, then how can we calculate the S?
So you need to calculate the denominator first, and then you need to calculate the inverse matrix. Inverse matrix. It's already complicated. So I suggest you need to use the kinds of the MATLAB or any other math tools, and they can provide the matrix, the inverse matrix either.
Okay, thank you.
Okay. Yeah. Okay, so in case of the cubic materials, we can calculate elastic modulus based on these relations. It is also related to the matrix determination or any other things. It's a little complicated. Um, because yeah, let me show. I think it's a quotation on history. I will explain this one. So if you see this matrix, it is related to the determination first. We need to calculate the determination. I think like this one. If you, uh-huh. So yeah, right there. So all term is related to the tensor E1, the what is the E11, the strain 11 or strain 22 or that sort of things. So we based on the definition, E11 is related like that. At the time you can invert it in you can invert it and then calculate the, the inverse matrix. I think it is just very hard to calculate the inverse matrix and then we get the ring. Yeah. But it's really difficult. So I suggest you guys should use the MATLAB or any other mathematics tools. It's pretty easy, pretty easy. So we can based on the this matrix component, we can calculate the elastic modulus in these situations. Then, in these situations, alpha indicates the angle, the cosine angles between HKL and 100, and beta is cosine HKL 101 and cosine HKL 110. So we can calculate the angle component of here, and then we can calculate the elastic modulus. So here is an example of the tensor component of the C11, C12, C44 for the cubic materials, aluminum, copper, gold, and other things. So many people, many engineers already calculated, so we can use this. So Let me show how to calculate the elastic modulus for tungsten in the one unit. Just think about just think about 2 minutes and then I will go how to calculate. Okay, let's start. Okay, so if you see the this cube, this is 110, and then this is HAL, and HAL, so 110, right? Then, so we can calculate it alpha. What is alpha? Alpha is expressed like that, right? So what is it? What is this value? Okay. If you see this angle is 45 degrees C, so you can say sine 45 is think 1 over root is correct. That in the way, one same, right? Um, um, so is 90 degree is 0. Okay, so we can bring this equation, then we can calculate the S11 first. S11 is here, 6. And 2 is minus 0.7 minus 0.7 times 4, 0.66. And then we know there are gamma, right? Would you please calculate? Alpha, alpha, beta, gamma is 1 is equal to 1/2 to 2. We don't need to consider this part because gamma is 0. So can you calculate this? Please calculate this part. 'Did you get it? It's 0. I think 0. This one is 0.33, and if we divide by 0.66, it is 0. So it's 2, 0. So we have one instance. So finally, And do you have any question? No? Okay, then we go on to the next page. So in case of the hexagonal crystals, the elastic modules could be expressed by only the gamma. Gamma is the directions to the z direction. Z direction. So okay. The only z directions 0, 0, 1. So it means in case of hexagonal structures, the elastic modules would be was affected by the gamma, only gamma, perpendicular case. And then um, the hexagonal crystal would be isotropic everywhere. And the base, according to the Janus ratios, if it is close to the one, it means the crystal structure is almost the isotropic. So in case of titanium carbide or tungsten or aluminum, it looks like very close to one. It means they have the isotropic properties. But if you see the nickel, copper, or iron, or zinc, they have a very large number of the Janus ratios. It means they have the very large anisotropic properties. This is so if in case of because the elastic modulus is attributed to the interactions between atoms. So if we focus on the kind of microscopically the molecular scales, the elastic modulus could should have the anisotropic properties. Mechanical properties should be anisotropic. However, if we analyze the crystal structures of the materials, the bulk scale materials, there's a lot of the grain boundaries. It means some molecular interaction could happen this way, but some molecular interaction have this way, even though they have the same crystal plane. Because of that, the mechanical anisotropic properties of materials could be averaged out. So they're gonna be averaged, and then they have their isotropic properties. However, if we prepare the single crystals, kind of the single crystals, they show the anisotropic properties. It's very important. But usually, crystal may have the poly crystals, lots of the grain boundaries. Um, we don't need to worry about the anisotropic properties. However, in case of the in case of the semiconducting process, they should consider the anisotropic properties because they have the very always they have the single crystals, such as the single crystal silica or single crystal. So they have the different if they have a different lattice, crystal lattice, there's mechanical properties should be different. Mhm. So this is temperature difference of the elastic moduli. If we there is a kind of a very simple method to describe the uh, temperature effect. The reason I just put it in here is if we just think about the semiconductor. So this is semiconductor substrate with single crystals, single crystals, and then if we just make it the and then they're gonna make the latch of the heat here. So because of the summer expansions, some different summer expansion, there is the kinds of the lasting modulus. But since the silica has a single crystals, we can reduce the mechanically generated defect. So we can design this crystal structure of the silicon single crystals, the dielectric layer or the metal part. We can decrease the defect generation when the transistor is working. When transistor working, the temperature could be increased because there is a hot spot and then some expansion could happen, but it could be released out according to the silicon crystal structures. Okay, so the temperature difference is related to the this one, the attraction force and repulsion force. But if we increase temperature, this point would move to this way. So because of that, some expansion could happen. Some expansion could happen. So because of the expansion, the stress could be generated, and it can make it. It is very important the semiconductor industry. Um, yeah, this is the kinds of the melting temperature of the materials and young soldiers. It is follow the is very similar trend in the almost linear relations. However, harrowing material uh, cannot improve the stiffness significantly because they cannot be mixed completely. They cannot be mixed completely. However, in case of the carbon nickel system, they can be mixed easily. So usually they made the Cu 7A and nickel continuing 2 years. Because of that, they can increase the elastic modulus in country because of their mixing together very well. Okay, do you have any question? No, okay. I'd like to start today's lecture, and then we are going to have the exam one this Thursday. This Thursday, um, this Thursday, yeah, they're gonna have the presentation, and then next Tuesday they have a presentation. I will follow the disorder. So please uh, prepare the presentation, and then if you, I will send the kinds of the reference paper. But if you want to use your own bodies or papers or any other document, feel free to let me know. I will switch it. Okay. So thank you for coming to the lecture, and then yeah, we are going. One more thing. Next is Tuesday. Please turn in the summary notes for the homework two. Uh, I announced it. But okay, I will check your emails and I will reply right now. I'm sorry. I'm sorry. Let me double check. Okay, thank you. And it's because I have the lots of the work, the due date, the proposal due date is next week, so I'm really sorry. Almost I got a lot of email to almost 100 or 200 emails for each day, so I missed your email. I'm really sorry about that. I will check it and then I will reply. Okay, thank you. Okay. Okay, thank you.
Thank you.
Mhm.
Thank you.